Hi all, this is Mr. Un here. Alright, I hope this short little video will help you to understand the topic of magnetism for science physics a little bit better. So let's get ready. I hope all of you will have the handout with you in hand. This will make this video a little bit more helpful if you have the handout with you. Alright, okay, I guess you're done. Now let's start moving on. Okay, for this part of the video, I'd like to just focus on a few areas, which is the first 3 points on the specific instructional objective. I think for this video, I'd like to address the needs that you need to pick up. You need to be able to state the properties of magnets, describe what is induced magnetism, and to distinguish between magnetic and non-magnetic materials. This is the 3 key objectives for this particular video. Alright, then let's move on. Alright, okay, magnetic and non-magnetic materials. Right, we will start with this point, the third point actually. Right, it is essential that you know and recognize when you're given a problem, what materials are considered magnetic and non-magnetic. Now, in the first place, what does it mean by magnetic? Magnetic simply means that this material, it can have a magnetic property, meaning that it can have 2 poles, north and south pole, and it can actually attract other magnetic materials. Okay, now for O-levels purposes and for a lot of common cases, you'll find that these are the 4 materials or metals that are magnetic, meaning that they have a magnetic property: iron, steel, nickel, and cobalt. Take note, iron, nickel, and cobalt, they are actually elements, metal elements, and steel is actually an alloy of iron. Right? How about non-magnetic materials? These are basically any other materials, whether is it metals or non-metals, that do not have any magnetic ability, meaning that they cannot be attracted by a magnet at all. Okay, so for example, wood, glass, cotton, copper, or brass. So now let's look at this question: are all metals a magnetic material? Then I think you should know by now the answer would be of course a no here. Alright? Right, let us move on to the next slide. Okay, now this table shows you what it means by magnetic and non-magnetic materials in more details. Alright, I'd like to draw your attention to this particular area regarding the alloys. Right, in chemistry you have learned that alloys are basically mixture of different metals, and as I mentioned earlier on, steel is basically an alloy of iron and carbon. Alright, there are other kinds of magnetic materials called alnico, which is also an alloy, and this is an alloy of aluminium. If you take note of how they actually get this word alnico, it's a combination of the first 2 letters of the 3 words: aluminium, nickel, and cobalt. Okay, alright, so these are some examples of that. Now moving on, we'll move on to the other point, which is the properties of magnets. Now there are 3 key properties that you must remember at all times. Now, first one would be all magnets have 2 poles. All magnets will have 2 poles. Right, one of them we call it the north, which is always seeking the north pole of the earth, or geographical north pole of earth, and the other one is known as the south pole. The south pole will always seek the south pole or geographical south pole of our earth. Right, so how do we know? Very simple. When we suspend a magnet, okay, horizontally, you'll find that it will always end up pointing the same way, meaning that the north pole of the magnet will always point towards the north pole of the earth. If you think about this carefully, in terms of magnetism, actually the Earth north pole is actually the magnetic south of the Earth magnetic field. Now we will talk about this in a while. Okay, we'll just skip this. Okay, now moving on. This is a diagram of what I just mentioned earlier on. North pole of the magnet, which is over here. Okay, it will always point towards the geographical north of the Earth. This is the geographical north of the Earth. We are talking about the Arctic and countries which are near to the North Pole, like the Greenlands and all that. Okay, so by the law of magnetism, which I will talk a little bit more in a while, I think by now you should know that the law of magnetism simply says this: like poles will repel, unlike poles will attract. So since the north pole of a magnet will always point towards the north of the earth, it will mean that the north of the earth is actually magnetic south. Okay, is equal to the magnetic south pole of a magnet. Okay, moving on. Now, the other properties of a magnet is that you find that there are two regions where they are strong. The poles of the magnet are two regions where the magnetic attraction is strongest, and take note, they are not exactly at the end of the magnet itself. Okay, the next slide will tell you will show you what I mean. Okay, right, this is how we determine if or the position of the north and south pole. Okay, now although the letters are written or marked near the end of the magnet bar, you'll find that the location, which is slightly further away from the end, shows that it has more paper clips. It can attract more paper clips. Therefore, the actual north pole will be somewhere here, and the actual south pole will be actually at this particular location, a little bit further away from the end of the magnets. Okay. Next, this was what we were talking about. I was talking about earlier on, the law of magnetism, which is simply this. Okay, O-level science physics will often ask you to just write down or state the law of magnetism, and this is what you just need to write out word for word. Like poles repel, unlike poles attract. Okay. Right. Diagram demonstrating what we mean by the law of magnetism. Right, this is suspended piece is actually a permanent magnet. So if I had to place another magnet or move it nearer to the north pole, it will actually push the north pole away, therefore suggesting a force of repulsion. If I had to flip the magnet right now, as the picture at the bottom demonstrate, you'll find that it will actually move the north pole of the suspended magnet nearer to the south pole. This demonstrates that there's a force of attraction. Okay. Right, now the next slide is regarding a testing of a magnet. Now, before we do this, I would like to skip on to this area called magnetic induction. So let's go to slide 14 before we move back to slide 12. Right, now magnetic induction is a process whereby a magnetic material, okay, a magnetic material that has not been magnetized yet has been forced to become a magnet, a temporary magnet, when it is placed in the magnetic field of some other magnets. Okay, this sounds a little bit weird in that sense, a little bit conflicting. So let's move on to the next slide. Let me explain with this slide 16. Right, so okay, so what's induced magnetism? Let's look at this example here. Now I think by now you should realize that on the left hand side, which is a permanent magnet, there exists actually an invisible magnetic field around this permanent magnet. So I'm going to draw it out this way with the red marker. Okay, let's say this is the invisible magnetic field. If I had to place then the iron rod near to this permanent magnet within or inside the magnetic field of this permanent magnet, you find that this iron rod will become a temporary magnet. And since it is placed near the south pole of the permanent magnet, the left end of the iron rod will be induced with a north pole, while the right end of the iron rod will be induced with a south pole. So therefore, we call this induced magnetism because the iron rod is now a magnet, although a temporary one. So what do you think will happen if the iron rod is being removed from the magnetic field? Well, I think you have guessed it. If you move the iron rod away from the magnetic field of this permanent magnet, the iron rod will return to its normal self, meaning that it's no longer a magnet again. The north pole and the south pole will disappear. Alright, now moving on to this, the next slide. These are other examples of induced magnetism. Okay, so let's have a look at the diagram on the left hand side. Two iron nails, both of them are magnetic materials. However, since none of them are already magnets, therefore there will be no attraction between the iron nails. Now let's look at the diagram in the middle. When I place these two iron nails within the magnetic field of this permanent magnet, what happens? Well, since this iron nail that is nearest to the north pole end of this bar magnet, look what happens. It will be this nail will be induced with magnetism, and not only that, the side nearest to the north pole will be induced with a south pole, the furthest away with the north pole. Now, so this first iron nail is now a magnet, a temporary magnet, and since it's a temporary magnet, it has a magnetic field around it, which then affects the second iron nail. It will cause the second iron nail to be induced again with magnetism. Since this end is nearer to the north pole, it will be induced with a south pole, and the furthest end will be a north pole of magnet. Okay, right. So what happens next? If I have to remove the bar magnet, look at what happened to the iron nails. The first iron nail is no longer possess magnetic ability, and therefore the second iron nail will just fall off. So therefore we call this the induced magnetism. We term this as what we mean by induced magnetism is lost. Okay, now let's move back to slide number 12. Okay, right. Slide number 12 is regarding testing a magnet, where very often you find that there will be a problem given to you whereby it says, hey, this is a magnetic material, an iron. How do you determine whether this iron is already a permanent magnet or is simply just an iron bar? Alright, so how do we find out whether this iron bar is either a magnet or it's not a magnet? The only sure way to do that is through the test of repulsion. Okay, only when repulsion occurs between the iron bar and a permanent magnet, we can say for sure that the iron bar is a magnet. Now let's look at the next slide. Right, let's look at a diagram over here. The first diagram at the top. Right, I suspend first a bar magnet and I move unknown specimen near to the bar magnet. Right, the specimen itself, if it were to demonstrate a force of repulsion, meaning that the suspended bar magnet were to move away, we can say for sure that this specimen is indeed a bar magnet. It's already a magnetized iron piece. Okay, and the fact that it moves away suggests that this specimen, this particular end of it, is also a north pole. Okay, so since there's a repulsion, we know that the specimen has to be a bar magnet. Okay, has to be magnetized. Now let's look at the diagram at the bottom. So what happens if there's a attraction? Well, attraction can simply means either of two situations. First, the specimen could also be a bar magnet, however with the south pole on the left end and the north pole on the right end. So when you place them together, you find that there's a force of attraction. The other possibility is that this specimen could just be an unmagnetized iron bar. Since the specimen is placed near the magnetic field of this permanent bar magnet and is near to the north pole, therefore we know that from our concept of induced magnetism, this end of the specimen will be induced with the south pole and this end will be induced with the north pole, therefore causing a force of attraction again. So as you can see, if we see attraction between a bar magnet and a specimen itself, we cannot conclude that this specimen is magnetized. We have two possible explanations. One, which is it is still an unmagnetized, it is an unmagnetized magnetic material, or it can still be a bar magnet. The surest way is to determine whether there's any force or repulsion. Okay. Okay, so that will end our part 1 of this magnetism. Okay, I will move on to part 2 in a while. Right, thank you for listening.